Welcome back. We are now going to talk about inner products and inverse of complex matrices. What does inner product reveals? Well, let us have a vector v, and then we now know how to add vectors with each other. v1 and v2, they are assuming they are vectors, and we know how to add them. We also know how to multiply a scalar with a vector. What else can we do with vectors? Well, we need to know the relationship between, let's say, two vectors, v and w. And we want to know the angle between these two vectors. To do that, we use something called the inner product. And we use this notation, the angle bracket, with two entries. And out comes a number. And this number is called a field. And these numbers can be complex or real. And if it is real, then we have a real inner product, and if it's complex, we call it a complex inner product function. Right. To understand this inner product, first we review what is a real inner product, and then we compare its difference between to the complex inner product. The most common real inner product that we all study is A dot B. Well, what does A dot B do for us? Is B transpose A, and this out comes a number. And this number, when A and B's are real, this number is also real. And what are the properties of this inner product? Well, A dot B comes out a real number, and what about B dot A equals to A transpose B? It actually comes out with the same number. So A dot B and B dot A, they are symmetrical. So this is the first property of what is required of an inner product. That when we do thus x comma y and y comma x for inner products, they are the same. Now we have a second requirement that that needs to be satisfied for real inner product, which is the linearity in the first argument. What does linearity in the first argument means? So now we have a more complicated form. We have x, y, and z, and we have a scalar a. And this scalar a belongs to f, and here now we're talking about real inner product. So a belongs to the real, and x, y, z all belongs to, let's say, Rn. So if we have a scalar, for example, 3x plus y, and these are inner product with z, then it is the same as 3x comma z inner product plus y comma z, and this is the same as 3x comma z plus y comma z. And you realize that if we are using the dot product, 3x transpose z plus y transpose, I shouldn't say, it should be the other way around. It should be z transpose x plus z transpose y. Now you'll realize that if you substitute as the dot product, then this property of linearity in the first argument is satisfied when you try to do it as 3x plus y dotting with z. Okay, you can prove it to yourself that this will be true, and when this is true, it is called linearity in the first slot or the first argument, where you can break the complicated first argument into its simpler components. Now, the other two requirements of real inner product is this: non-negative definite means that when we send x an inner product with itself, it must be a real number that is positive or equals to 0. And the last condition is that the positiveness, saying that this can be only equals to 0 when we send the 0 vector in. And when we do this, the inner product always giving us positive number allows us to use norm. So really the norm of x is typically defined as the square root of the inner product. Okay, the square root of the inner product of the same element, since this is always positive, then we can take the square root equals to 0 only when x is the 0 vector. So the norm is defined as the length, and the length must be greater or equals to 0. Okay, now we have figured out what the real inner product is, and we realize that these 4 properties are being satisfied by the dot product. What about the complex inner product? What changes? Well, you realize that, hey, the real inner product means we are defining this operation of v times v over the real field. What does over the real field means? Alright, let's go and take a look. Here, where's the real number that is going to help us change things, or becoming the complex number? So only the scalar a is required. You see, in the real inner product, the scalar a belongs to the real. In the complex inner product, the scalar a belongs to the complex number. X and y are vectors, and of course typically these vectors are now Cn. Okay, so we are going to see what are the 4 conditions that are needed to define that this is a proper complex inner product. So the 4 of them are, the first requirement is that it's called conjugate symmetry. It means that when we take the inner product of x and y, then it must be equals to the conjugate of y comma x. Now, this is different to the real inner product. The real inner product is x comma y equals to y comma x. It basically means that the output number is real. There's no such thing as the real. If there's only the real part, the conjugate of the real part is still the same real part. So the real inner product is symmetrical, while the complex inner product requires that the inner product produce a number for x comma y inner product, and when we take y comma x, this number need to be conjugated for them to be equal to each other. So we call it the conjugate symmetry. Now, the rest, in fact, of the other key requirements of inner product is the same. It is still linearity in the first argument, same as the real inner product, non-negative definite, meaning that when we send the same vector into the inner product, we'll get a number that is real and must be greater or equals to 0. And the last one is that it must be equals to 0 only when we send the 0 vector in. So this shows us, this defines what the real inner product and the complex inner products key requirements are. You can take a look at the Wikipedia as well as this Stack Exchange, which discusses the difference between the dot product and the inner product. Thank you.